All right, so I suggest we start if you're ready, Bart.
Yes, I am.
So today we have the pleasure to welcome Bart Jacobs in this seminar on program logics and applications. So the first two seminars uh, were already devoted to presenting verification tools that build on program logics. So we saw Pharmacy WP, presented by Logiques, which is basically a Hoare logic or even a Floyd logic for C. And then Yannick Moy presented Spark, which is a deductive verification tool for the Spark subset of Ada, and that includes mostly Hoare logic, but also with handling of pointers, for instance, reminiscent of the Rust programming language. And so today we are going to hear about VeriFast, which is another very nice deductive verification tool. And this one is strongly grounded in separation logic, even concurrent separation logic, and applies to C and Java, and has some extremely interesting approaches to deductive verification in general. So thank you, Bart, and please, up to you.
Thank you very much, Xavier, for inviting me to this to lecture at this lecture series. So the structure of my talk will be as follows. So first, I will try to summarize the highlights or the main points about VeriFast in one slide. Then I will quickly go over the industrial proofs that we have done between quotes. We haven't done really big proofs yet, unfortunately, but we have done some non-trivial industrial proofs. And then what are the main research results that we have obtained using the tool, and some ongoing research that we're doing with the tool. And then we go into the main part of the talk, which is going to be a demo of all of the features of the tool, or most of the features of the tool. So what is VeriFast? So it's first of all, still a research prototype. It's not a commercially supported tool, definitely. It's also not yet in all ways industrial strength, I must admit. But you can do some nice things. So it's for sound modular formal verification. So it's modular verification, one file at a time, not whole program verification. It's supposed to be sound. There are some bugs, known and unknown, but if we fix those, then it should be sound. Of course, that's a very big story in itself, and I will get to that in the ongoing research. So it's for verification of C and Java programs, but we are looking at other languages as well as ongoing research. And we do so by symbolically executing each function or method separately. So one function is verified independently of the implementations of the other functions. And we do so using a separation logic specification of each function. And we use separation logic also for representing memory during symbolic execution of each function. And one of the main properties of VeriFast is that it is indeed rather fast. It's typically quite within seconds that it would give you an answer. And the reason is very simple, because it doesn't do any significant proof search. It typically doesn't explode in any way. So it's really a rather dumb tool. And that's the advantage of that, is that it is fast. The user, so to make it fast, the user needs to provide loop invariants and other proof hints. So the tool doesn't need to do very much itself. So what have we done so far? One thing we did is, so the Belgian government provided this Java card program to developers for testing their applications to run against the Belgian electronic identity card. So every Belgian person has an electronic identity card, and on that chip is a Java card program. And so some version of that program was provided to developers, and we have verified that this program doesn't have illegal, so out of bounds array accesses, and also works correctly in the presence of card tearing. So if you tear your identity card out of the terminal while some operation is going on, it should still maintain the invariance of the card. So we verified that, and we did find a few bugs in that version of the program. We also verified a home gateway routing program from some telecom company, so to be run in home gateway devices at customer locations. We only verified memory safety and data race freedom, and we also found some data races in this program. We verified the simplest Linux device drivers that we could find, so some keyboard and mouse device drivers. It was a big job because it uses the USB API of the Linux kernel, which is a huge API, so it took us a lot of time to model that and understand that. And we also found some bugs that were fixed in these device drivers while we verified that. And then very recently, Nathan Chong at Amazon Web Services used VeriFast to verify the core concurrent queue data structure of the FreeRTOS real-time operating system. So that's also a nice result, not by us, but by someone else. So that's even nicer. So he was able to verify also some functional correctness properties of this concurrent queue data structure. So except for the last one, we only verified memory safety and data race freedom. So then in the research, we look at trickier programs in general, but smaller ones, of course. So one thing we've looked a lot at is fine-grained concurrency specification. So how can you modularly verify programs that use fine-grained concurrent data structures, such as so-called multiple compare and swap data structures, or data structures using atomic machine instructions, such as compare and swap, and those kinds of things. We've looked at how to verify programs that unload parts of themselves during runtime, such as the Linux kernel that can unload device drivers at runtime. How can you verify that you don't have dangling function pointers, etc.? We looked at how to verify that programs that have exception handling, so Java programs, whether they still maintain their safety invariance, and also whether they are still have their liveness properties that you want. And I think we found that most Java programs probably do not maintain their safety properties or their liveness properties when they do any kind of exception handling, or even if they use multi-threading at all, then they probably don't have these properties because of the way Java's exception handling works. It doesn't actually make it easy to maintain those properties. And we proposed a language feature called fail boxes to remedy that. And we also proposed some proof rules in separation logic for reasoning about those constructs. And then we also looked at how to verify termination of programs that have dynamic method binding. That is, object-oriented programs with virtual methods. How can you modularly verify termination of these programs? And all of these things we implemented in VeriFast to test them on larger programs to see if these ideas were actually applicable. And when I say larger, I mean 1,000 lines instead of just 10 lines like you do in a paper. And then absence of deadlocks for programs that use monitors with condition variables, so wait notify or wait signal patterns, or advanced patterns using channels. So if you pass channels along other channels and then you perform blocking receives on those channels, can you then still prove absence of deadlock of those programs? So we proposed some results there. How to specify and verify modularly the safety and liveness of the I/O behavior of programs. So we finally recently were able to verify hello world. So that was a big step forward for us. And not only that it actually prints hello world if it prints anything, but also that it will actually in the end print it. So that's the liveness part of that. And then in ongoing research, we have three. So there's one piece that's almost done, which is busy waiting. So how to verify termination of programs that use busy waiting to wait for, so where threads use busy waiting to wait for other threads or to wait for external events. So that's actually, that was submitted to CAF, and we're of course awaiting the notification on that. Then much earlier work that we're still in the early phases of is a big one that I think might be interesting to Xavier as well. So we're trying to hook up VeriFast to CompCert, and we're trying to get successful VeriFast runs to generate cock proofs that the program is actually correct with respect to the CompCert semantics. That's what we had hoped to finish a Hello World version of that before this talk, but we're actually not yet quite ready for that. But I think within a few weeks, we might have been able to generate a cock proof for some very simple, very fast verified programs with respect to CompCert. And then we're also looking at supporting C++ programs. So we're hooking Clang in front of VeriFast as an alternative to our own parser that we wrote ourselves for C and Java. So hopefully this will also help us support more C programs actually. But the engineering effort is already turning out to be a huge part of the work. So we hopefully we'll get around to some actual research results on C++ in addition to just the engineering. We'll see about that. And then we're starting up also some further work on verifying both the free RTOS real-time operating system itself, as well as applications running on top of free RTOS, trying to verify interesting properties of that. So actually some industrial contacts told us that that's what they would very much like. They said that they have a very hard time testing their free RTOS applications and shipping them without bugs. And they were asking if we could help them get the bugs out of their applications. And then also looking at Rust, because it's a hot topic of verifying, for example, unsafe Rust code using VeriFast, for example. Okay, so that's the research we're doing using this tool. And in the rest of this talk, I will introduce you to the tool by means of a demo. So let's see. So this is the VeriFast IDE. And I've loaded a very simple C program into it just to get started. And if I want to verify it, so it declares a variable I, initializes it to 10, increments it, checks if it's equal to 11. Of course, this should verify. If I press the play button, indeed, it will say it's verified. So how does this work? We can step through it. So it will do a symbolic execution of it, and we can see what happens at each point. So initially it assumes the precondition, so this will end up at the assumptions. Then this will execute the declaration, so we will get a local variable I with value 10 here in the locals. We get I gets I plus 1, so 10 plus 1 becomes the value of I. In general, this can be a term that has symbols in it. Here it's a ground term, but in general it can have symbols. Then we get an assert, so we ask the SMT solver. In this case, we're using a Redux, which is an SMT solver that we wrote ourselves, a very simple partial re-implementation of the simplify SMT solver. But it's actually sufficient for most of our purposes. We also have a backend to, or link to Z3, so we can also use Z3. But for most examples, Redux is sufficient. So we ask the SMT solver to prove whether 10 plus 1 equals 11. Of course, that will not be a problem. And then we're done. So then we have to check the post condition true, which is of course not a problem. And then let's look at a more interesting case where we have an argument. And then we say if x is less than 0, x is minus x, return x. Let's try to verify this. first, of course, have to provide a specification. Let's first try requires true, ensures 0 less equal x, for example. And of course, we get an error here, because if x is min int, so then the least possible value of int, then the negation of it is outside of the bounds of type int. So we have to say here, or int min, I should say, int min less than x. And then it goes through, I would hope, except it doesn't. No, I should of course say 0 less equal result. There we go. So here, there are two symbolic execution branches that are done by the apps function, verifying function apps. So the symbolic execution tree branches, of course, off into two branches. In the first one, we assume x is less than 0, and then we go through the function under that assumption. And in the second one, we assume x is not less than 0. So here you can always tell on which branch you are. So VeriFast doesn't try to join symbolic execution paths again. So every conditional construct that you encounter during execution branches causes a branching in the symbolic execution tree. In theory, this can blow up and this can become exponential, but in practice, we see rarely that this causes performance problems. Okay, so that was a very basic program. Let's look at something that uses the heap. So this is a program that declares a struct counter with a field x, and it declares functions for creating a counter, incrementing it, getting the value from it, swapping two counters, disposing a counter, and then a main function. But the initial version of this main function doesn't use any of these functions. So it allocates a struct counter, it initializes it to 10, the x field. It reads the x field again, checks that it's still 10, and then terminates. So this is fine, right? This program, it should just verify. Or does anyone see a problem with this program? Well, let's ask VeriFast. Let's just press play. VeriFast says that there is a branch of the execution of this program where this memory access is not allowed because there is no so-called no matching heap chunk. So whenever a program tries to access a piece of memory, VeriFast looks for a so-called heap chunk in the symbolic state, in this part of the symbolic state called the heap chunks. And a heap chunk represents the permission to access that piece of memory. So when you're trying to access the x field of a struct counter instance C, then VeriFast is going to look for, I'm sorry, a heap chunk counter underscore x at address C with some unspecified value. And it doesn't find that in this case, and that's because we're on a branch where malloc fails. So it doesn't actually allocate any memory, it returns a null pointer, C equals 0, and in that case, you don't actually get any memory permissions. So we can fix this program by writing if C equals 0 abort. And then it should be fine, right? Then this program has no problems. Well, let's ask VeriFast again. Actually, it still has a problem, at least if you look at it modularly, not as a whole program verification. Then this function, which happens to be the main function, leaks heap chunks. It allocates some memory without freeing it. Of course, if the main function does that, it isn't really a problem. But this function is verified like any other function. And it allocates some memory without doing anything with it. So some chunks are left in the symbolic heap at the end of the function, which is considered an error by VeriFast. So the chunks here are the permission to access the x field of the counter struct C. and also the permission to free that struct, because you can also allocate structs on the stack and then you're not allowed to call free. So this malloc block counter chunk gives you permission to call free on that pointer. And so that's what we should do. We should insert a call of free. And if we do that, then symbolic execution does terminate normally. So we can step through it again. So we say run to cursor. We put a cursor at the closing brace. We say run to cursor. And then we get the list of steps here of a symbolic execution path that reaches that point. And then we can step through that. So again, we first assume the precondition. We perform the malloc, which in this case will produce two heap chunks. So the permission to access the X field and the permission to call free. Then we get to an if statement. In this case, we're going to be on the else branch. So we again get that C is not 0. Then we initialize the X field. So the value, the second argument of the counter X chunk will become 10 instead of this symbol, this fresh symbol value, which represents the initial unspecified value of that field. So this chunk is replaced by this chunk. And then when we read it back, we also get the TMP variable, which will have value 10. So then we can check that this is equal to 10, which is of course not a problem. Then we free that pointer. So VeriFast will look for these two chunks and remove them. Now they're gone. And then we check the post condition and it's complete. All right, now let's use some of these functions that we defined higher. So instead of allocating the struct counter here, let's call create counter. Sorry, like that. And then we have to fix the spec for create counter because it has a requires false. We'll have to weaken that precondition a little bit. Let's make it true. So now if we do that, so when you're using VeriFast, it's easiest to just do the least possible thing that you can do to fix the current error, and then the tool will tell you what the next thing is that you should do. So let's run again, and then it will complain that the create counter function leaks heap chunks. So create counter allocates the struct counter, but doesn't do anything with those chunks. And in this case, of course, what we should do is not free them, but pass them to the caller. And we can pass them to the caller by putting them in the post condition. We just mentioned the chunks, of course, with the right names for the variables in the post condition, separated by this separating conjunction. So it's the star in the literature, it's just a star, but I put ampersands around it to distinguish it from multiplication. There we go. So now if we run execution, symbolic execution again, it succeeds. So the post condition, so at the end of verifying this function, the post condition is consumed. So all of the chunks mentioned in the post condition have to be present in the heap chunks. They are removed. And then the leak check happens to see that there are no chunks left. And then at the call site, when you execute the call of the function, let's see how that works. So if we get to the call of the function, VeriFast just looks at the spec of the function. It first consumes the precondition, and then it produces the post condition. It generates the chunks that are mentioned in the post condition. And then it just goes on. All right, so then we can also apply the inc function. So now the value of C will be 1, not 10. Similarly, we'll have to fix the spec for inc first. So let's put true here again. Again, let's do the simplest thing possible to fix the current error. And then we get an error here because we're trying to access a piece of memory for which we don't have any permissions. And in this case, we'll have to ask for permission from our caller. So we can use the counter X syntax here, but we can also use a nicer syntax, C arrow X points to. So this is the syntax used in the literature on separation logic, points to, and then something. So we can just say, we know that it points to 0 here, so let's put 0. And then, of course, we have this chunk still there at the end of the function. We got it from the caller, but we didn't give it back. So we need to give it back to the caller at the end. So we have to put it in the post condition as well. And here it's going to be 1. So this works, but of course, this is not a very nice spec for ink. We want it to work for more different kinds of initial values of C arrow X. So we can put a question mark here to bind the current value to a ghost variable called value. And then we can use that in the post condition to say now it's going to be value plus 1. And now if we try to verify this, of course, it's not going to work. We get a potential arithmetic overflow here. So here we have to say and value less than int max. And now it goes through again. Okay, so now we can use get instead of directly accessing this field here. Again, the spec is too strong, or the precondition is too strong. So we want to ask for permission to access CX. We have to give it back with the same, in the same state. And we also have to mention here that our result is equal to this value. So if we have that spec, then it goes through. By the way, get doesn't require full permission for this chunk. And to say that we only need to read that chunk, we can ask for a fractional permission by putting in square brackets before it a fraction or a coefficient for the chunk to say that it's sufficient to pass in some fraction, which gives you read permission, but not write permission. So if this chunk was shared among multiple threads, for example, you could still call get on it. We'll get back to that later. So this still works. And then finally, we can dispose. We call dispose instead of free using the dispose function. So let's see what dispose needs. Well, it needs the thing it's going to free. It needs the permissions that it's going to get rid of. And here we don't care what the value is, so we put an underscore. But that's not enough. It also needs to know that this is an allocated memory block and not a stack allocated memory block. So we need a malloc block counter of C. And if we have both of these, then it goes through. All right, so now we have encapsulated the data structure so that the main function no longer has to access the internals of the data structure directly anymore, but the specs used to verify the main function still reveal the internal state or structure of the data structure. So now we want to perform some abstraction. We want to describe this API abstractly, and we can do so by introducing separation logic predicates. Predicate counter, struct counter C, and value, or let me just put a comma first.
Donc, voilà, c'est bien ce que je pensais. Ici.
And so then we put here simply the chunks that we want to hide from the specs. So here we put counter X.
Oui, sur système. Non, ça va, y a pas de souci.
Forcément, ça prend compte.
So I'm hearing you guys.
D'ailleurs, là, il m'entend. Là, il m'entend, donc c'est bon. Un tout petit peu plus de volume, ce serait parfait.
Excuse me? I'm hearing you whispering. I don't know if that's...
No, I'm sorry, we had a little short technical problem, but this is being fixed.
Okay. So what we want to do is we want to hide these particular chunks. And we do that by simply copying them into the body of this predicate. Counter of C, like that. And now we can replace these two chunks in the post condition of create counter by simply counter result 0. So this predicate is just an abbreviation for its body. So now we haven't changed really the meaning of the post condition. If we now try to run again, we do get an error. So when VeriFast, at the end of verifying create counter, when it tries to check that all of the chunks mentioned in the post condition are present, it says, I can't find the counter chunk. So it only finds these two chunks, which are not counter chunks, but they are the constituents for a counter chunk. So when you define a predicate, you define a type of chunk. And so it has the constituents for this chunk, but not the chunk itself. So all that needs to happen now is to fold up, which is called closing in VeriFast, the definition of the counter chunk. Close counter C0. And by the way, I can put that after the return, which is sometimes useful if the return expression has a side effect. But I can also, in this case, put it before, which is more what you would expect, I guess. And now it goes through. At least the create counter goes through. So now I have to also use the counter chunk in the inc spec. So here I have to say counter C value. Counter C value plus 1. And then also for get, counter C value. Value and result equals value, and then dispose underscore like that. Let's see. I have to open. Here I have to open the predicate. Open counter C, because I have the counter chunk, but VeriFast is looking for the counter underscore X chunk. It's inside of there, but VeriFast by default doesn't look inside of other chunks. But in a moment, we'll see that you can make it do so for simple cases. So now this goes through, but again, you need to close it up again for the post condition. But this becomes, of course, tedious, and therefore VeriFast allows you to mark a predicate as precise by putting a semicolon between the input arguments and the output arguments. And then whenever you supply values for the input arguments, VeriFast will automatically try to close and open the chunks that you're looking for. So if we put the semicolon, the rest just goes through. You don't have to explicitly put any open or close statements. This just goes through now. Okay, so that was a very simple heap data structure. Now let's look at a slightly more interesting one. A stack. A stack built using a linked list, which is the bread and butter of separation logic. It's the textbook example. So let's apply it here. So we have a struct stack with a head pointer, which is a pointer to a node, and the node has a next pointer and a value. So let's describe that using a predicate. And to describe it, we'll also need to describe the contents. And to describe the contents, we need to first define a mathematical data type of lists of integers. And in VeriFast, so I just had learned Coq, so I was inspired by the Coq syntax. So I use the same keywords as Coq, more or less. So you can write inductive ints, for example. Let's call it ints. Is either empty or ints with a first, with a head value and a tail, which is again an ints. So we define the inductive data type ints with two constructors, empty and the non-empty constructor. This would be called nil and const in a regular definition. And actually VeriFast has a list data type built in, a generic one. But here I'm using this one for illustration of how to define your own inductive data types in VeriFast. Okay, so now we can use that in the predicates. So predicate nodes, struct node n, ints values. So either n is a null pointer, and in that case values is empty, or it's not a null pointer, and then we have a chunk giving us permission to access the next field, and it has a value next. You can access the value field. It has some value. There are going to be more nodes at next that have some values, value 0. We also have permission to free the node n, and our values are the consts of value and values 0. So this is how you can define recursively the linked list nodes built from struct node instances. And using this recursive predicate, we can now define the stack predicate. So let's see. Maybe I can make it a little bit smaller. Predicate stack. Struct stack values, stack head, and block stack. We have some nodes starting at head with values. Given these predicates, we can now specify the functions of the stack. So create stack takes nothing and gives you back a stack at result with contents empty. Stack push takes a stack at stack with some values in it and returns a stack at stack with the specified value inserted at the front of the given values. Stack pop takes a stack with some values. They should not be empty, so it should be of the form ints value values, and it returns a stack with just the tail of the original values. And the result of the call will be value. And then when you dispose a stack, you have to pass in a stack with some values and you get nothing back. So now we can actually verify already this main function that creates a stack, pushes two elements onto it, pops them again, and checks that it gets the right values out. Well, actually, we can try that at least. Let's see what happens. So stack create stack and stack push went through, and notice that I put semicolons here so that VeriFast automatically tries to open and close the predicates. But at stack pop, that didn't work out. And the reason is that, so if we look in the symbolic heap at this point, so it has a nodes chunk. So the value of variable head is head 0, the symbol head 0. And we have a nodes chunk at head 0. And its value is not empty. But still, VeriFast does not unfold the nodes chunk to find the value field of the first node in that list of nodes. And the reason is that VeriFast is very careful to remain fast. And since this chunk is only in there in the case when the pointer is not a null pointer, and it doesn't know that this pointer, the head pointer, is not a null pointer, it won't open it. Actually, there's a lemma that says there's a property of this node's predicate that says that if the list is not empty, then the pointer is not a null pointer. But VeriFast doesn't deduce that lemma automatically. So you have to here explicitly unfold the nodes chunk and say, you have to open the nodes chunk to find the chunk that you're looking for. And then it just goes through, except that we also need a loop invariant here in this loop that disposes all of the nodes of the stack. So here we have to say invariant nodes at n. That's all we need here. And then it goes through. Okay, so that was still a very simple data structure. And to illustrate another feature of VeriFast, let's look at a slightly more complicated data structure still, namely a queue. So here, this is already provided with annotations. So this already goes through if I just press play. And but let's first look at the C code. And whenever you're doing a VeriFast proof, quickly it becomes very useful to ignore the orange parts first and just look at the pieces of black and blue that are in between to just first understand what's going on in the C code. And so this is a queue implemented using a linked list as well. And it has a pointer to the first node and to the last node. And the last node is a sentinel node. So only the nodes up to the last node, but not including the last node, have the actual values, the actual elements of the queue. And this way we can efficiently add nodes to the end in constant time. But to describe this shape, we cannot use the nodes predicate that we used before. We have to use a list segment predicate, which is the classical predicate of separation logic, of course. So I think you've seen this in an earlier lecture in this series. So the list segment predicate takes a pointer to the first node and to the last node, but not, this is, this describes a list segment starting at first, but ending directly before last. So the last node of the list segment points to last as its next pointer. So that means that if first equals last, then it's actually an empty segment that's being described. So its values are the empty list. And otherwise you have the chunks for the first node, and you have a list segment starting at next going to last. And the contents of the entire segment are the value of the first node followed by the contents of the tail. And using this LSEG predicate, you can describe the queue. So the queue has the first and the last field. And you have a list segment of nodes from first to last. And you have the chunks for the last node, for the sentinel node, and we don't care about the value of the sentinel node. And now we can try to verify the enqueue function. But when we try to do that, we run into a problem. So the enqueue function creates or allocates a new node and then sets the next field of the last node, so the node pointed to by last, to this new node, and then tries to set the new node as the new last node. So then this old last node, this old sentinel node, becomes part of the body of the queue, and it should now be described by this list segment predicate. But here we cannot change the structure of the, so if we go here now to this place and we look at the state of, let's see if I can grab this, sorry, I have a problem. Need to I have a problem here. Let's see. I need to pull this up. There we go. So here is the contents of the symbolic heap at this point. It has a bunch of chunks. So it has an LSEG from first to last, and it has a node from last to n. But what we need in order to close the Q predicate is an LSEG from first to n. And we cannot obtain that by simply closing the LSEG predicate, but because the LSEG predicate is defined by recursion by adding a node to the front, not by adding a node to the end. So to prove this, that this is equivalent, we need an inductive proof. And to do inductive proofs in VeriFast, it's like writing code. You just write a function, a recursive function, like a C function, except in an annotation. So here we have the LSEG add function, which is just written with the same syntax as any other C function, and also verified in the same way, but with the keyword lemma in front of it and inside of comments. And VeriFast will check that this function, that any function that you write in annotations actually terminates. And then you can just call it also in an annotation. So here we're calling LSEG add, and it actually will put this extra node at the end. So it takes an LSEG from first to last and a node from last to next, and it gives you back an LSEG from first to next. And it does that by recursively calling itself on the tail of the LSEG. And this recursion terminates because in this case, it's easy to see you're doing induction on the derivation of the original LSEG predicate. And VeriFast can tell that, and therefore it allows this recursion. So this is the use of lemmas as inductive proofs in VeriFast. That's a major feature of VeriFast. That's the way that you can do induction in VeriFast. Okay, so this is queues and lemmas. So now let's look at concurrency. So this is a very simple HTTP server. So by the way, Xavier, I forgot how much time I need to leave for questions. So how much time do I have left for my presentation?
Oh, let's say maybe five or 10 more minutes, and yeah, normally we stop at 15 past noon, but then we can take some more questions after that.
All right, thank you. So then I will just indeed go through this concurrency example, and then I will round off. Okay, so let's first look at the C code itself. So this is a very simple web server. So it has a main function that creates a string buffer where it will track all of the requests, the HTTP requests that have come in. It protects this string buffer by a mutex. And then it creates a server socket at port 80 and sits in a loop, accepting incoming connections and then starting a thread to handle those connections. And the thread that handles the connections, it simply reads the first line from the input from the connection. It acquires the mutex, appends it to the buffer of requests, to the log of requests, and then releases the mutex, prints this log of requests, so a copy of it to the connection, and then closes the connection. And we can try to verify that. It actually doesn't work because I have to put a command line argument. Now it works. So this actually goes through, so it means that this program does not have data races. And of course, this follows automatically from the fact that you're using concurrent separation logic, as you have learned today, I think. And so how does this work exactly in VeriFast? So first of all, how does mutexes work? How do mutexes work? So if we look at threading.h, which is the threading API that we are using in this example, and then if we look at the specs for mutexes, they are here. Like that. So when you create a mutex, you have to provide a so-called mutex invariant, which is going to be like the resource invariant, as it was called in the original concurrent separation logic paper. So there's a separation logic predicate that describes the resources protected by the mutex. And you have to pass it in. So VeriFast does not support ghost arguments, so you have to pass them in through the symbolic heap by creating an instance of a predicate called create mutex ghost arg, passing an argument as an argument to that predicate, the actual predicate that you want to supply as the mutex invariant. The contents of that create mutex ghost argument is just true, so it doesn't actually contain anything. The nice thing is we can now pattern match on that, and then we have a name for this predicate. So the ghost argument is actually P. Then we require P, so we consume P. So when you create a mutex, you consume the mutex invariant, and then you get a chunk stating that this mutex now exists and that it has mutex invariant P. So you get full permission for the mutex when you create it, but when you want to acquire a mutex, you only need fractional permission, of course, because multiple threads should be able to try to acquire the mutex at the same time. They should be allowed to race for that mutex. So, so this allows you to match on the fraction, the particular fraction of the chunk that you get here. So then when you actually acquire it, you get the mutex held chunk, saying that the current thread now holds this mutex, and you also get access to the contents protected by the mutex. Then when you release the mutex, you have to hand back in those resources. You have to hand them back, the permissions for those resources, and you get back your fraction of the mutex chunk. And if you want to then, if you join all of the threads that are using the mutex and you reassemble full permission for the mutex, you can dispose the mutex and get back the contents free and clear. So that's what's happening in the HTTP example. Well, actually, the latter part is not. The threads are never joined. But when the mutex is created, the lock invariant predicate is passed in as a ghost argument, and the definition of the lock invariant predicate is as follows. It describes the requests global variable here, pointing to the request string buffer and the string buffer itself. So these two chunks are protected by the lock invariant. And then, so once you have created this mutex, you go into this loop, and the loop invariant also describes that you have this mutex. At this point, you have it only with some fraction because you've already handed parts of it to the threads that you have already spawned off. And then when you start a thread, so this is using higher order programming, using function pointers. So how does VeriFast deal with function pointers? Well, one way to deal with it is using so-called predicate families. So let's look first at the definition of thread start. In threading.h, here, the non-joinable threads are the ones I want to look at now. So non-joinable threads here. So thread start takes as arguments a run pointer, so a pointer to a function to run, and some data to pass into that function. And for the run function itself, it needs to know that it is a thread run function, which means that it satisfies the thread run type def. So VeriFast allows you to associate a specification, a pre and post condition, with a type def that defines a function type. So this is a C type def that defines a function type that takes a single argument of type void pointer and returns void. And it allows you to associate a pre and post condition with that. And by saying is thread run, VeriFast checks that this function actually satisfies that spec. And if we go to HTTP, then we see that handle connection has been annotated with a function type annotation saying, claiming that handle connection actually implements the thread run function type, and VeriFast will check that this spec is compatible with the spec of thread run. So then the is thread run fact will be true. And then secondly, the data that you pass in has to satisfy the thread run data predicate family, which means, so this is a predicate family, which means you can give it a separate definition for each value of the index. So this predicate family indexed with this particular run function has to hold for the data. And if we look here, we define an instance of that predicate family for the index handle connection to specify the resources needed by handle connection. And these are then consumed at the place where thread start is called. So here we close thread run data, and at the place where we implement handle connection, we can open thread run data for this index to get those resources. All right, so now I'm running over time, so I'll end here, and I'll be happy to answer any questions that you have.
Okay, well, thank you very much, Bart. It was a very nice talk and a very impressive system that you've demoed in front of us. Let's see, maybe I can even show my face. All right, so do we have questions? I see some in the chat, but maybe you can just turn on your microphone and ask them, or while I'm going through the chat. Yeah, so Jean-Christophe Filiatre had a question about storing values as a ghost field in the struct stack. So I guess, can you have ghost fields in your data structures? And I'm not sure what Jean-Christophe wants to do with them, but.
Right. It's possible in any case. So I can put here int foo, and I can assign any value to that. That works. And it's very useful in concurrent, when you have concurrency, it's very useful to be able to define ghost fields. Because then you can share these fields using fractional permissions between multiple threads as well.
Okay, so yeah, Jean-Christophe tells us that he would use that to store the list values, which I guess is the abstract mathematical list of values. Would that work? Would that help?
Well, that's not the way you would do it in VeriFast. In VeriFast, we use this predicate argument here to convey the contents of the stack.
I see.
Yes.
Well, maybe we have questions in the audience too. There are a few people who are here.
Hi, Bart, it's Xavier Leroy. Thanks for the very nice demo. I'm curious, would that help to use ownership to simplify annotations where ownership applies? Since you said you're looking at present.
Definitely, of course. If we have ownership information in the type system, that's what you're suggesting, right? Like in Rust, for example, then we can treat these. Then we can treat more things like just being on the locals here instead of being in the heap. So then you don't need to mention chunks for these things in your specifications. So it becomes just like a primitive value in your specification. So that would simplify the specs. Whether it would really make a big difference in terms of proof effort, I'm not sure. It would just be more concise, I think, the specs.
Actually, I had a question. Prompted by a remark by François Potier in the chat. So François was impressed about the leakage detection in the C program, and I told him that's a normal feature of linear separation logic, non-affine separation logics. But then I remembered that you also support Java, which is a garbage collected language. So I guess you also have an affine version of your logic. And what does it make a big difference, or is it just a switch that you flip somewhere?
Yes, it doesn't make a big difference. So in Java, I simply don't do the leak check at the end of each method. So whatever chunks are left, I just discard it. But
for instance, it makes no difference from for the proof search techniques, or deciding when you want to unroll things, or
no, because I
kind of things.
There's not much of that anyway in the tool. So, yeah.
All right. Any other significant differences between the Java and the C version of the tool? Well, I guess, well, C has an awful memory model, but, well, apart from that.
Right. Yeah, and actually we don't really support that completely yet. So we're not entirely sound with respect to C's real semantics at this point. We still have a naive view of C semantics. But well, I mean, Java has object orientation, of course, but we deal with that very similarly to the way we deal with function pointers, as I showed in the example, with indexed predicate families. So in Java, they are indexed by class names instead of being indexed by function pointers. So you can define instance predicates within a class and then override those predicates in the subclasses. This is actually a technique proposed by Matthew Parkinson.
Okay. Well, there are still more questions coming in the chat. I don't know why people don't want to ask them live. So continuing the GC question, someone asks if whether in Java we can force a given predicate to be linear, because the GC doesn't handle all the resources and some resources still need to be linear.
So VeriFast doesn't support that. But you can, of course, program it yourself in a way by explicitly tracking the presence of these resources. So, for example, one thing we do explicitly track is which locks are held, because we support verifying absence of deadlocks. So actually, you could see it in the HTTP example. And you can use a similar technique for other resources that you want to track. So if you look at the spec for start thread, so thread run says that the thread will start with an empty lock set and will end with an empty lock set. This will force you to free or to release all of the locks that you held. And you can apply a similar technique for other resources that you want to track. Of course, this becomes a question mark for modularity, right? So how you abstract over these things if you have function specifications.
All right, so some more questions from the chat. So Loïc Corançon is asking about the code to lemmas ratio in complex programs, because he's afraid that the automatic open close may not work well for complex programs. So probably you would have to put more open and close annotations yourself. Is that something you've experienced?
Definitely. I mean, in complex code, so for example, these fine-grained concurrent data structures that we've done, there the code to, or the annotation to code ratio becomes in the order of 10 times as much annotations as code. So you have 1,000 lines of annotations for 100 lines of code. And that's very normal if the code is very complex. But of course, these are data structures that were picked specifically because they were so complex. If you have a regular business code, so to speak, where nothing much interesting is happening from a programming point of view, then of course the annotation to code ratio is much more reasonable. And what I mean by that is, if we have one line of annotation per line of code on average, then we consider it reasonable. So that's
all right. Yeah, well, some of those data structures are complex indeed. So, okay, so there's another comment from François Potier about keeping track of log sets that could be painful because it introduces the need to prove distinctness of logs. So is this a practical problem?
Well, I mean, the way to get around that is to have this order, and you need an ordering anyway to prove absence of deadlocks. So you can prove distinctness as a side effect of proving ordering, right? One log is less than another, then it's also different from the other. So, and it also allows for modularity. And actually, in a recent paper, Toplas 2018 paper, we proposed a way of doing modular specification of modules that use locks in such a way that you don't actually have to reveal that you're using a lock inside, by exploiting the ordering of the modules and reusing that for the ordering of the locks used by those modules. So I think we have a nice story.
Okay.
I'm not sure I can really explain it in this space, but yeah.
Okay, well, yeah, that sounds nice. More questions in the audience? No. So yeah, I skipped over a nasty question from François, so let me use that for the last question. So he's asking about the Java memory model or the C11 memory model. So do you have any plans for relaxed memory and then those atomic, supporting those atomic constructs?
Right. So, well, first of all, for sequentially consistent atomics, that's fine, that works fine. I've looked a little bit at doing x86 TSO.
Mm-hmm.
So I have something for that, but it's quite nasty. So I haven't actually published, I have a TR on that, but nothing published. It's too ugly, I think, to really propose. But no, on the even more relaxed ones, I don't have a clue how I would start in supporting that in VeriFast. No, that's completely open for me.
Okay, well, no more questions? No, the chat is quiet. So, well, thank you again. And thanks a lot, Bart. This was a very nice and instructive talk. So, thank you
Very much for having me.